Good day everyone, I'm Czar, and welcome to Math in Action, when we uncover the hidden power of calculus in our everyday lives. You might think that calculus only lives inside classrooms, but it's secretly shaping the world around us, even in something as simple as turning coffee. Looks like we already found something. Excuse me, mind if I ask what you're doing?
Oh, I'm just waiting for this coffee to cool down. It's too hot to drink.
Classic morning problem. But did you know that your coffee cooling down is actually a real example of calculus?
Calculus for coffee?
Exactly. Let me show you something.
You leave this coffee on the table, something interesting happens. Coffee slowly cools down until it matches the room temperature. This is called Newton's law of cooling, and it's actually a differential equation, which means it uses derivatives to describe how temperature changes over time. The formula for this is dt equals negative k, open parenthesis, t minus ts, close parenthesis. But as time goes on and the coffee's temperature gets closer to the surrounding air, the difference becomes smaller, and the cooling slows down. That's why the graph levels off, and the coffee finally reaches room temperature. Now, let's proceed to the formula. dt by dt equals negative k times the quantity t minus t sub s. By solving the differential equation using integration, we get this formula. It predicts the temperature of the coffee at any time. So calculus doesn't just explain why a coffee cools. It can actually calculate its exact temperature at any moment. And that's the power of calculus. It turns everyday moments, like waiting for coffee to cool, into something you can measure and predict.
Perfect temperature thanks to calculus.
It's not going to be long like a coffee cooled down perfectly. What are you gonna do with the cup?
Simple. It's time to show my shooting skill.
That's right. It's like you wrote these little tattoos. Calculus? What does calculus have to do with blowing a coffee? Just take it up. That's another idea this way.
When you threw the cup, it didn't move straight. It followed a curved path called a parabola. That's what we call projectile motion. And calculus helps us describe every part of it. Let's start with the basics. The cup's velocity has two parts, horizontal and vertical, which is v sub x equals v cosine theta and b sub y equals v sine theta minus gt. To find out how fast it moves at any moment, we have derivatives. The derivative of position gives us velocity, and the derivative of velocity gives us acceleration. dy over dt equals b sub y, and d squared y over dt squared equals negative g. This means gravity constantly changes the vertical velocity. That's why the cup goes up, slows down, and comes back down. But what if we want to know where the cup will be at any given time? That's where integrals comes in. Y equals b sine theta t minus 1 half gt squared, and x equals b cosine theta t. By integrating velocity, we get position, meaning calculus helps us predict the cup's exact height and distance through time. That's how we can trace its entire curved path, the arc of motion. So if you calculated correctly, you have made it in every perfect throw. It's not just aim, it's calculus in motion.
Okay, folks. Now that you have seen the math behind it, are you ready for a calculated reply? Let's give calculus. From cooling coffee to toasting cups, calculus is working on our us, helping us measure, predict, and understand change. We saw how Newton's law of cooling uses calculus to describe how temperature changes over time, and how projectile motion uses derivatives to predict the path of a moving object. But here's something to think about. If calculus can explain motion and temperature, what other parts of our everyday lives might it be shaping you?